takes a bit longer than expected. So just, you know.
We can go without slides. Yeah, I mean, we could. I mean.
There is a chance. But
That and then.
so plug your VGA in there.
Look at that. The wonders of dongles. Oh, and then. Is that really the problem?
What?
We'll just go. All right, cool. Built-in retina display. All right, cool. Go away. Coexisting preferences. That view. Enter full screen. Yes. All right. Sorry.
Hello, everyone. So a bit later, and unfortunately only locally and not remote, we're starting the tutorial on TLS 1.3. Please be prepared. You need to fill in a survey after this session, and it's very important for us to see how we can make the tutorials and the other work better. If this is one of your first 5 IETFs, please join the session on Thursday morning early to give us from the education team tips and tricks on how we can make your first IETF experiences better. And now with further ado, because we already lost a bit of time, I'll give it over to the TLS working group chairs to tell you more about TLS 1.3. Cheerio.
Thanks, Niels. That survey is actually the last slide on the last page on the agenda or in the presentation. Since we don't have to record this, we are going to go freeform and walk around with our own microphones and go back and forth. So this is going to be very exciting. So this is the TLS 1.3 tutorial. Thanks for coming. I want to note that there's more than a few of you in the audience that probably could teach this. So, let's keep the questions at the appropriate level.
And that's Sean.
I'm Sean.
I'm Joe.
And he's Joe. All right. So what are we going to do today? We're going to do the whats, the wheres, and the hows of TLS 1.3. All right. We promise, right? Not too technical, because we didn't know what level of people we were going to get here, whether you're going to be super cryptographers, people that designed this protocol from day one, or people that are your first IETF. So we're kind of going for like the middle ground. Lots of links. So everywhere everything's underlined, it's a link. So you can click to it, get to it easier. Also, some little lame nerd humor every now and again. The other thing is, if you're here to argue your newest, greatest extension for TLS or argue about some particular interesting working group topic at the time, we're going to cut you off. We're going to do that on Thursday or not at all. So just keeping it, that's the level playing ground from there. Joe?
All right, so here we have, whoa, all right. Here we have kind of a brief history of SSL and TLS. So back in the early 90s, Netscape came out with a protocol called SSL, and the first version that was public was 2.0. And then Microsoft also had a protocol called PCT, or I think it was Personal Cryptographic Transport, maybe, 1.0. These two protocols were brought to the IETF. Actually, I think it was SSL 3.0 that was brought in, and SSL 3.0 was kind of adopted by the working group. But when the working group adopted it, or over time, the name SSL was replaced with TLS, and that's what we have today. And over the past, 10, 20 years almost, wow. We have had numerous versions of TLS. Probably the one you're most familiar with now is TLS 1.2. But now we're working on 1.3 and soon to be finished, we hope. I did put up here QUIC, which is a protocol developed by Google, a new transport protocol, and there was part of that was QUIC Crypto, or is QUIC Crypto. QUIC Crypto heavily influenced the design of TLS 1.3, and they're kind of moving forward, I guess you'd say hand in hand in the IETF, where if I could pronounce it correctly, QUIC Crypto is going to be replaced with TLS 1.3 in the standardized version of that protocol.
So the only thing I would add, if you're an RFC nerd and you look at the numbers and go, why is the RFC for SSL 3.0 so much later than some of the TLS versions? It's because they came after the fact at the end and said, we've got this historical document, let's just publish it to get it out the door. So we helped get it out the door and just get it actually immortalized, as opposed to being on some Mozilla website or, Firefox website from way back in the day.
Okay, another thing we want to emphasize is that, hey, there's a lot of implementations of TLS 1.3 already in the works. People have had interoperable versions for some time now. A lot of them are based on draft 18, which was at the beginning of this year, but draft 21 is the current one, and we have people experimenting with that right now. And this has given us a lot of insight into how the deployments of TLS 1.3 will go in, which will hopefully ease the transition from 1.2 to 1.3.
And this just shows the open source stuff. The link to who's implementing it actually shows that the number of browsers. I believe every major browser has said that they're going to support it, and there's even test servers available. This is probably out of date because the hackathon started yesterday, and I'm sure that some of them are on later versions. So that's just kind of an FYI. We did these slides like last week, so they're old. So where are the specifications? So the working copy is on GitHub. Now, whatever, it's great, it's a working copy. But the interesting thing is that because we did that, we've gotten so many more useful inputs from people who don't even come to the IETF or participate in the working group. And it's not just like, hey, you go change this, they actually provide text. So it's been really kind of an interesting experiment. If you look at the contributors section, there's like 50 plus people listed there. And those people actually provided concrete text that went in there. Into the draft, and it was really kind of cool because we have a much, I would say, broader set of people that actually looked at the protocol. And then the official ID version is actually at the IETF website, and again, you can follow the links. All right, so where does this sit in the stack? This is the great little picture. Some of you are all kind of laughing, right? Well, first thing, of course, we're in the internet, so we got IP, then we got some TCP, and then look, it fits right in there in the middle. X marks the spot. And the application layers go on top. So, okay, pretty straightforward, right? Well, what does it do? Well, this is the famous XKCD, right, about how you get computer scientists to actually talk about security. And there's Alice and Bob and Eve, Eve's the person who's passively listening to this stuff. So what are we trying to do? Stop Eve from passively listening to things, so we encrypt the communications, right? The other protagonist is Mallory, right? This is the active attacker. They're trying to modify text. They're trying to break the communications, so we try to protect against that.
So yeah, it's protection against both information disclosure, so confidentiality and integrity. So it's important to note that with TLS 1.3 in particular, there's more emphasis on having those two things work together.
So people are like, well, the TLS protocol, actually, there's 4. In previous versions, there was even more. We got the handshake protocol, which essentially sets up the key exchange stuff. We got the alert protocol, which basically kind of provides like errors and the like. And the application data, which is where the applications go. And then the record protocol, which allows you to multiplex all of these things across the top. And that leads to an interesting observation. Is that, wait a minute, what do you mean? You can just use some of it, and that's what Quick's basically going to do. What's wrong with the previous versions?
So over the past, starting in, say, 2012, there was a lot of research done on TLS, and so we started to see a lot of problems being found that had to do with some of the cryptographic construction, some of the particular features like renegotiation and the way we did CBC mode ciphers. Compression has showed problems like in breach, and then different key exchange mechanisms had slightly different problems with them. And so over time, security protocols show their age and they tend to weaken, and the flaws become exploitable potentially. So what we do in TLS 1.3? So one of the top priority or driver for TLS 1.3 is probably security. It's a security protocol, okay? But what people really get excited about in TLS 1.3 is that it's faster than its predecessors. So we'll see why later, but this is a primary design motivation. And then finally, privacy is a critical consideration of TLS 1.3, especially since during the development of TLS 1.3, there was the disclosures made by Snowden about potential pervasive monitoring, and this was one of the things that guided the design of 1.3.
So why is it more secure? Thank you, security researchers. Basically, these guys were getting famous, putting up logos and websites. We were having like bad days. My phone was ringing. I was like, is this going to be on the front page of the New York Times? Oh shit, let's call some people. Sorry. And basically, we tried to figure out how we could change the economics of these guys to do their reviews earlier rather than later. And they very graciously bought off on it because they said, how do I publish? So we set up a symposium for NDSS thanks to ISOC, and there were some other conferences that got together that reviewed these things. They got to publish papers. We have like 10 plus papers that reviewed the things. These guys are like in the design of the protocol, and so we're much more confident. We've got formal methods that are used, both done by hand and through multiple automated processes to actually check to make sure that the protocol is secure. So we're much more confident that it's actually a better design protocol, and it actually provides the services that it said it does.
And part of that design process was to make sure that the protocol was analyzable. So that also influenced some of the design, is to try to make it such that you could do formal analysis on it.
So how do we make it more secure? RSA key exchange. So we took that out. So about a decade or more ago, RSA said, stop using it. So we finally listened. I remember when we did this in Seattle, we all stopped, took a breath, came back and said, are we going to do this? And we said, sure. There are some implications. Stream ciphers. The one we had was busted. Finally took it out. Not saying you can't put a stream cipher back in TLS 1.3, but the one we had was bad, and it was thanks to Andre Popoff and some movement to actually get an RFC published to get that done, to actually move the industry to get off of that. Compression.
Yeah, so compression is shown to bring about vulnerabilities in the protocol, because if you compress the data and you can influence what data gets sent, you can kind of see over, if you can basically get some disclosure of information. So we've removed compression from the protocol itself.
If you're paying attention, you will notice that there's a certificate compression draft that is related, but that's just specifically compressing one part that we know about, so because it's the biggest part actually of the handshake.
Renegotiation. I don't know how many people remember the renegotiation problems, but it turned out renegotiation was insecure for a long time until somebody figured out, hey, this doesn't work the way we think it does. Or at least applications weren't using it the way we thought it does. And so to avoid problems with renegotiation in the future, we've removed that part.
Block cipher, block cipher, block cipher. Got him out of there. Turned out that there were lots of attacks. At one point I was joking with one of the researchers if they had a stack of logos made, and he smiled. I took that as a yes. So, gone. And obviously SHA-1 is getting sunsetted. So we basically just took it out completely. All right, the other approach, KISS. I don't know if you've ever seen Adam Langley's state machine diagram, and he talked about an IETF, I don't know, I can't remember, I think it was in Dallas, and he put up this state machine which was like the spaghetti. And we're like, all right, let's get rid of some of that. So we took out a bunch of things. So basically when we look at the record payload algorithms, we were like, let's use modern cryptography. That means AEAD, and it's AEAD only. If you come with another algorithm that's not AED, thank you very much, you're not getting it. Key establishment, we basically went for as best as we could get, which is like ephemeral Diffie-Hellman stuff, or PSK, or both. Essentially, it's one or the other is mostly specified now, but the document does allow you to do both. And
so we also converged many of the protocol design elements around session resumption and pre-shared keys and session tickets. These were all very similar types of operations, so we kind of combined those mechanisms into one. Previously, these were all in separate drafts, so they've all been incorporated into, well, I guess PSK and session resumption and session tickets were all in different drafts. They've been converged into the base spec and improved. The actual security of session tickets has been improved, and PSK as well. In addition, it turns out that the zero RTT mechanism, which we're going to talk about later, a little bit of a spoiler, is also kind of part of this converged protocol architecture.
All of it making it easier to implement, apparently. And then ciphers. I don't know if you're an IANA geek and you like to go through the IANA registry, there are hundreds of ciphers there, multiple hundreds. Here we're really talking about the block ciphers, but there's like over 100 in TLS 1.2. Don't really need all those. We got it down to 5. Probably expand in the future, but right now we just got 5. And it's much easier to implement. So what algorithms supported? I always thought he was a handsome dude, so we put him up there. AAD algorithms only, right? So we got ASGCM, CCM, and SHA-CHOP 20 poly 1305. For elliptic curve stuff, we got the P256, P384, 512 curves, and then we have the 25519 variants and the 448 stuff up as well. Thanks to DKG, we got some nice named FFDHE groups, and we only support RSA PSS signatures on certificates. The one exception, obviously, is for the root certificates, which can be the regular PKCS version 1.5 stuff, but that's just for the roots. I'm sure this list will expand, but again, if you're not AAD, go away. How do you specify ciphers?
Yeah, so how many people here are I guess this is probably not the best audience for this, because I know a bunch of you know exactly what that cipher suite string is, but usually I go to the audience and say, okay, who can tell me how to read that old cipher suite string?
What's SHA-34?
Yeah, that's a new truncated
You
version.
don't know. I thought you knew all these things. So yeah, it should be SHA 348, 384?
384.
384? But so actually that's the hard part too, right? Because SHA 384 is not the integrity algorithm like you might expect with an AD algorithm that actually represents the hash used in the key derivation. But the exciting thing about TLS 1.3 is that we've kind of went away from this monolithic Cipher suite string to more of an a la carte specification of Cipher suites where we have just that traditional Cipher suite field that you might be familiar with now is just used for the bulk encryption algorithms, for that encryption and authentication or integrity protection on each packet. That now is specified only on the Cipher suite string or the Cipher suite string and the Cipher position in the protocol only specifies the bulk encryption. Key exchange and authentication, these are all represented in TLS extensions now, so they can vary independently of the encryption algorithm. This gives us a little bit less of a combinatorial explosion in Cipher suite, so that actual 300 Cipher suites would actually could be represented in TLS 1.3 in a lot smaller number of code points. But we hope that we don't try to exercise that capability as much anymore.
So the only other thing to add, I guess, is that no, that's probably good enough. And the other, if you go and look at the IANA registry, you'll see that there's this huge list of things. The new way, it's obviously, we're using the same registry, but the code points are slightly different. So what we decided to do also was kind of include this recommended column to basically say these are the working group / IETF blessed algorithms, and if you want your National Cipher Suite, Vanity Crypto, whatever, you can have those, but they're not going to be marked as recommended.
Does that mean I can have my own Cipher Suite?
You
Sean?
can, absolutely, if you want. You can get them however you want. They're just not going to be a working group. Because we ended up with the problem where people were incorrectly using the IANA registries to essentially grade implementations. You didn't support all 305 algorithms. Please add X algorithm. Totally not the way to do it, so we wrote a draft. Actually, Joe and I wrote the draft. I tried to get other people to do it, and that's the plan, is that we'll be able to indicate the algorithms that the working group thinks are the right ones, essentially. Okay, so remember we said it was faster? Seriously, okay, great. How fast? So if you look at 1.2, there's the handshake mechanisms. I simplified it a little bit. But basically, you got to go through 5 things, essentially, before the client can start sending the application data. In 1.3, it's 3. So that's money. Like, think of it that way, right? It's also good for IoT devices because there's less time. It's got to be up, the whole 9 yards. Goodness, that's awesome. And that's basically the HTTP starts here. We did this because that's one of the main protocols where it's used.
Yeah, I mean, so in terms of just the round trips, it's usually 100 milliseconds or more when you're talking about an intercontinental, packet round trip. So this is pretty significant compared to, computational cost of doing this.
So what are the normal modes? This is where it gets a little bit more complicated. So in one RTT, you'll note it's not really one round trip, but whatever. There's the different coloring. So the purple stuff is the key exchange stuff. The server params is, parameters essentially is set up. The authentication stuff is like the certificate verified, cert request message, and the finished. And then the application data is obviously the application data. The stuff that's shown for the purple stuff right now, this is the normal way it'll be used basically, where you give your Diffie-Hellman share in. There's other extensions that you can include. We didn't want to list them all because we weren't sure we were going to have time. Looking at my watch, we may have had time, but I think this is probably the normal mode for how things are probably going to end up working.
So for session resumption, once you've already spoken with the server once, you've negotiated some keys, this key material can then be used to resume that session without having to do the full cryptographic handshake. This helps in reducing the amount of computational complexity, so it's good for IoT devices or for just regular connections. You'll see also that this has been merged with the pre-shared key mode, so this is how if you're doing pre-shared key, you could also establish your session through this mechanism. And you'll also notice that this has both a pre-shared key and a key share. This means that pre-shared key could be used in combination with the Diffie-Hellman key agreement to get fresh session keys or forward secrecy even in PSK mode.
That was a spoiler alert.
Yeah.
All right, so seriously, is that all you got? Can you make it go a little bit faster? This is where it gets to go to 11. We got 0 RTT, right? It's still not 0 RTT, but the idea is you can start firing off application data from the get-go. You've already connected to the server, you saved key material, you can basically fire it off. So HTTP starts from the get-go. PFS, however, only starts there, right? Unless if you didn't use the optional key share stuff at the beginning, that's where it goes. The problem is there be dragons here. Lots of dragons. So if you're an application, this is the go fast button, but you don't just turn it on and it all works good. If you didn't think about it and you didn't do it right, didn't do some analysis, you're going to fall on your face. You're going to be on the front page of the New York Times. Think about it. We've had a couple people that have actually done analysis for a couple things like, I know DKG DNS, somebody did something for NTP. I'm pretty sure the HTTP guys looked at this and think they're okay. But basically, if you're an application person who wants to use TLS 1.3, we put in the draft that you must specify how it will be used or if it will be used. It's okay not to use it.
Yeah, and even in, so for HTTP, when we look at that protocol, it'd be important to understand for web applications exactly when browsers are going to send that 0 RTT. So for example, a browser will most likely default to sending GET requests in 0 RTT if it's enabled on the server. In most cases, at least to begin with, it won't be, but certainly some applications will turn it on. But it's just a red light. If you see people saying, oh, we're just going to turn on 0 RTT, you need to make sure you understand the implications of that in your protocol and in your applications.
And I guess I can't stress this strong enough, that the working group is okay with how it's in there. I'm sure that as we go out of the working group, we'll have some discussions about this. But this is pretty much one of the requirements that we got from people. Make it go faster. If you can do that, do it. So we've actually come up with a way, but if you're an application developer, again, there's dragons.
Okay, so when we look at privacy issues, one of the areas that there has been concern about is in traffic analysis and the amount of information that the TLS protocol revealed to observers. And so some of that has been through the headers. There was the content type and version information as well as the length information was exposed. And in 1.3, we've decided that, hey, this information should be encrypted, should be hidden from view. And so that type of information is now in the encrypted part of the packet. There still is a sort of dummy header in order to make it easier to transition, so that middle boxes that require that header to be there will still see something. In addition, we've increased the capability to do padding, so you could have more ability to hide the length of the information you're sending. The spec itself doesn't tell you or give you any strategies on how to do padding to provide or thwart traffic analysis, because that's a fairly complicated and deep topic. But we give you the capability to do that.
Yeah, so that's, again, it's an optional feature that you can make use of. Some people would say you should make use of it. So remember that PFS thing? It's turned on by default. Again, it's kind of a big deal. It has some implications. Maybe
So-
we'll get the end.
Just in case, how many people are familiar with the term forward secrecy? Does anybody not know what the term forward secrecy means in the audience? So
I guess
yeah.
So the idea is if you send a bunch of communications and they've been encrypted and you break it at time t, you can't read the communications at t minus whatever. So you can't go backwards in time. So this is important to make sure if you have a break, you can't go back and read all the old traffic from however many days, months, years your friends have been copying it.
Right. So all the keying material is derived dynamically or ephemerally instead of using static information.
And so if you remember when we said the PSK mode, you don't normally get PFS, but if you can do it if you include the optional key share. So another thing is, hey, you're encrypting more earlier? What? So again, this is the kind of the four things that the protocol does, right? So the first one, obviously, it's in clear text. So great, but you got SNI and ALPN in there. So that gives you a little indication of maybe what's going on, where the packets are going. So some people are working on trying to figure out how to encrypt SNI. That work is still ongoing, and I would say they're still looking at the options that are available. Right. Still get PFS though, right? Because the part that comes back from the server to the client is encrypted. And what's in there? Well, your server ID and your session ticket. So there's a few implications there. And then obviously the part that comes back fully from the client is encrypted. And what's in there? Your client ID. So you're able to hide the server and client ID from people that are watching.
Yeah, and in previous versions of the protocol, that information was sent in the clear. So a passive observer could see the identity of both the client and the server. In this case, a passive observer would not be able to get the identity of either the server or client, and an active attacker wouldn't be able to get the client identity.
Yeah, I mean, the client ID could also include the certificate, right? So when you're doing certificate authentication, you can, it's encrypted. Because again, when you do the key exchange modes, because the client sent its key share and the server sent its key share, then obviously they got both and they can start encrypting. What's not to like? It's awesome, huh? There are some, I'm not going to go into all of them, but there are obviously some implementation differences because of the way it's been in TLS 1. Star up to 1.3 has been implemented, and you need to carefully consider what that means to you. Do you want to add anything?
Yeah, so I guess we would say that over time, if you look at TLS 1.2, the adoption of TLS 1.2, which was released in 2008, started like this. It was flat. And here's 2009, 10, 11, 12, and then we started seeing uptake. This was because in that time, the main driver for TLS 1.2 was security improvements. It wasn't until 2013 where people really started breaking and putting logos on and really increasing the visibility of some of the problems of the earlier protocol versions. Even though maybe those didn't affect all of the versions, but still there was enough to start getting people to think about moving to that latest protocol. In TLS 1.3, the motivation for doing the protocol is security, right? There's improvements in security. There's improvements in privacy, so on the internet, that's a big deal. And then there's also speed improvement. So this is kind of something we think will drive people to have it adopt much quicker.
And the other thing is the GitHub and the implementations, right? It's actually out there now and being used. So the way what we've been paused on actually being done is implementation experience, and they're looking at what issues running 1.3 would cause. And the way you do that is by running it on a large scale. Thank you, Google and Firefox, for helping us figure out the smart way to implement this stuff so that we're not just kind of blindly doing things like maybe we did before. We have some more real-world implementers actually doing things and testing it to make sure that it, hopefully when we get done with this, we can all take a big deep breath for a little while before going right to the next version.
Now, this is primarily, I would say, on the internet side of things. So on connections going over the open internet, we would expect to see more adoption quicker. For connections that are running in data centers, there are some of these features and the changes in the TLS protocol make it may make some of the operational practices some organizations use more difficult. And so there's continuing work on trying to figure out, okay, how do we make some of that experience better, or what needs to happen to make it easier to deploy in those environments. For some places, it's not going to be a problem. For others, it presents a big barrier. So that's kind of an ongoing topic as well.
All right. Related drafts. We got test vectors. Thanks, Martin. So the idea is that when we actually pump this out, that people can actually take the stuff and actually measure against it. They can use test servers, and they can actually use the stuff that Martin's got in his test vector draft. And it's so cool that it's set up that basically when they pump out a new version of the base draft, it just pumps out new versions of the test vectors. It's kind of neat. Obviously, if you've heard of TLS, you may have heard of DTLS, which is the connectionless version. We're still kind of working on that. It's still basically a work in progress, and the drafts for both of these, the working copies, can be found at GitHub, and the official IDs are there as well. The links to them, I mean. And the DTLS stuff, I think, if I'm looking at my crystal ball, I think it's going to go quicker because there's only a couple of issues that we really have left. And that's Thursday. We'll be plowing through GitHub and issues, so come and have some fun. So that really brings it to the end. They gave us an hour, and we kind of blew through that. Not nearly as fun as I thought it was going to be. Please feel free to grade us. And since we have all of this time, we'll take questions.
Yeah, please.
Luckily, there are some people in the room that actually might be the authoritative people to answer them. Hi, Bob.
Hi, very nice session. Thank you. So one question. I think the last ITF I went to one of the sessions, there was a lot of discussion about whether TLS 1.3 was more susceptible or less susceptible to people doing inspection in the middle. And so what is the status of that? And
the status of that conversation is that the proponents for the particular proposal at hand could not be here, and we've postponed that till London.
Yeah,
so it's not basically not going to, I mean, people are free to discuss it outside of the working group, but it's not going to be a working group topic because it seems like it would be unfair to have this conversation without the actual people that are proposing it essentially.
So,
but to kind of summarize what the discussion
Yeah.
is about, so TLS 1.3 and in particular the feature for forward secrecy makes it more difficult for the way people currently will do interception in their own environments to do that. Technically, it makes what they used to use, this static keys that they could put in their inspection devices, is no longer available. So there needs to be, if they want to continue to do that, they'll have to figure out other ways to do that. Now, one of the questions is whether you should do that or not. That's a very big topic.
Yeah, and what I will add is there was an original proposal. They heard feedback from the working group. They have discarded that proposal and have a new one that was updated based on working group input. Now, whether the entire working group agrees with that is another question, but that's not going to be decided till London, or at least discussed till London.
I guess the net result is TLS 1.3 makes interception harder, and that makes some people happy and some people sad.
okay, that was my question. So, but this is still an open issue.
It's still open and ongoing, yeah. But it's probably not going to be resolved on Thursday.
Right. Well, I didn't ask that question. But the kind of thing people do today where they provision certificates in the hosts in an enterprise, that sounds like it's harder than it was in the previous version.
Yes. So, for
Okay.
example, if I have the same, in a naive example, you could have the same private key for all of your servers, and then I could put that private key in an inspection device, and it could inspect all of the traffic. That doesn't work the same way in TLS 1.3.
Okay. Thank you.
A newcomer, great. Don't tell me you're a mathematician.
Yeah, I'm Paul Barrett. I have the purple badge of ignorance.
Great.
I just wonder, can you explain a little bit about what you're doing for Quick? Is that basically going to be built on DTLS 1.3, or are they going to be different?
So the idea is that it's going to be the same. That the idea is that you're only going to use, I love animation, but God, it's really hard to go backwards. It doesn't use the application data. So the idea is that it's going to use the handshake, the alert, and the record protocol to do the initial establishment, and then it's going to do exporters to do the following on crypto.
Right.
Okay.
So,
Yeah.
do you know? Is it going to use Is it going to use the DTLS-based handshake, or
TLS?
It's going to use TLS. So it will use TLS, but basically it uses the handshake portion to negotiate the key material, and then Quick will have its own encryption layer that uses those keys.
And updates mechanisms later. Yeah.
I suppose the question was, is Quick effectively going to be built on top of DTLS 1.3?
It's TLS.
Okay.
Yeah.
Thank you.
Going once.
Great overview. Thanks for doing this. I think these things are very valuable. Can you give a status update on the encrypted SNI work?
Sure. First draft got adopted since the last meeting, and right now it just basically lists some of the options that people have talked about, and that's really about it.
So for SNI, for any newcomers, SNI is server name indication, and so what happens is in the TLS protocol, when a TLS client is going to talk to a TLS server, many servers will support multiple domain names. And so what the client can do is say, I want to talk to joesgarage.com, and it can then, when the server receives that packet, it knows what domain on that server in a multi-hosting environment the client is trying to contact, and so it'll send the correct certificate back for that server. The problem with this particular protocol element is that it goes into clear, so somebody who's observing the traffic will see that information and know what host you're trying to contact. Privacy advocates are very concerned about this, that this could reveal some information.
So if Voice of America is fronting for, freedom for democracy in country X, then the idea is that you'd be able to, Voice of America would essentially be able to front for them, and you wouldn't be able to know it. But if you have it in the clear, you can clearly look at the first handshake that's going and block it.
So yeah, there is a working group app that's been adopted, and people are working through kind of some of the options on how to do this. We haven't settled on I would say we haven't really settled on a technical approach yet, but there are some very promising approaches.
Yeah, what I would say is that I guess a message was sent to the list that we canceled the Monday session, and that Ben Schwartz asked if people wanted to get together during that time to talk about it. So feel free to contact Ben on the list and see if there's a bar you can find to go drink beer at and talk about encrypted SNI. Or a room. I'll get you a room. Any other questions? Going once. Survey. Oh yeah.
Survey.
So go to the survey. I'm being told by my masters that it's got to be the survey. This is good. So this is the funny part is that a lot of times the presentations are awful dry in the IETF. I think we all need to improve on our public speaking skills, and it would be good that these would be slightly more entertaining and riveting. Hopefully we succeeded a little bit. I still think I need practice, but hey. So please fill them out. It'll make it better for the next time we have one of these for somebody. And next time we'll get a actual recording.
Yeah, and the working group meeting for TLS is on Thursday morning.
Thursday morning, 9:30.
The Monday session we didn't need to use.
We're not popping popcorn.
Just one other quick thing, since you brought up the surveys. The other thing we're looking for is ideas for other tutorials that people would find useful, and volunteers to give those tutorials. So
all right.
that's always appreciated.
Okay.
All right.
Thank you very much.
Thanks.